So I'm going to talk about a propensity score. I don't remember, have some of you already worked with a propensity score or not? Or no? No? Yes? Yes, okay. Okay, so if you want to add some comments, don't... So, well, from my point of view, which is really personal, you know, I don't know if you know that advertisement with a little boy in Darth Vader, and he's trying to influence his doll, his dog, his washing machine, and finally the car, and suddenly the car, you know, the light goes on, and that's fantastic. But, well, in fact, it's his father with the command. And I would say that that's me, that's propensity score, and that's the statistician. And you'll see, well, it's quite of a trick, or I wouldn't say a gadget, but it doesn't solve everything. I'm going to talk about basic reminders, but we already talked about it this morning, so I'll go quickly. And what are the principles of ideas of propensity score and the limits. So we already saw this morning that randomization was blocking the paths of confounders. And really, randomization gives you two comparable groups for every confounder, known and non-known, but only at the beginning of your study. And in randomized trials, one of the problems is to maintain this comparability. That's clear. So, and you find that in the famous table 1, you know, always looking at are both groups comparable, and you're a bit reassured. Okay. So that's the force of randomized trial. And finally, if you don't have any differences in characteristics that could influence the outcome, the only difference between the two groups is intervention. And so if you find an association, it's rather causal. Yeah, because by all means, on the other ways, the two groups were comparable. So the problem is, the problem is, can we evaluate an intervention in other types of studies and in observational studies? So this is an example who comes from the EPIPAGE cohort, EPIPAGE 1, and where they looked for prolonged sedation or analgesia and 5-year neurodevelopmental outcome in very preterm infants. And I'll take examples from that paper. So could we really look at an intervention in a cohort study? The problem is, why were some newborns treated by sedation, and why were the others didn't receive sedation? And so the problem is comparability in the two groups. In cohort studies, as I said this morning, the two groups are never comparable. And so interpreting the association at the end is a bit difficult. And peculiarly because the allocation is not at random. And for instance, maybe the most severe baby were sedated, and so you would conclude that sedation alters outcome. Okay. You can even make a DAG about this. Okay, just to this morning's talk. So they looked at neonatal characteristics, and effectively the exposed to sedation were much more severe newborns, and everything was statistically significant. So once again, we are between intervention and outcome, and between analgesia and 5-year outcome. So we're looking at analgesia, yes, no, and 5-year outcome. And the idea of propensity score, you could here adjust on a lot of confounders. But we have one first problem, is the parsimonious principle on putting so much confounders in the model. And so we don't know, even in adjusting on those potential confounders, if why they had analgesia or not. And so it doesn't resolve all the problems. So one way of doing it is to try and look after determinants of receiving analgesia or not. And so here it's a new question. It's in your cohort, what are the risk factors of being treated? So that's the first step. We're going to try to find which variables are linked, associated to the fact of being treated or not. And it's exactly the same thing as a multiple adjustment after looking at risk factors. Here we are just looking at risk factors of being treated. And so the aim of propensity score is to predict the administration of intervention, and there's a bit of modelization in that. And finally, the propensity score will give you for each individual a probability of being treated. So, for the first step, what you're doing is taking treatment as the explained variable and trying to see what are the variables who predict treatment. And that's where the statistician comes back. So they looked at that, and they looked at the crude odds ratio, what was associated to treatment or not. And then after they adjusted on many variables. And I would be a bit different, as I said this morning, because here you're really trying to model a prediction, and so you can be much larger on the number of variables. Of course, you have to have a big cohort. That's clear. But you can try to include more variables and be a bit less parsimonious. And as we said this morning, univariate analysis is most always flawed. And so we don't just take the variables that are associated at 0.05, but we take a larger criteria. So they took 0.4. It can also be necessary to have some variables transformed in your model. So here we're really in modeling and predicting a probability to be treated. So it's not the same spirit as looking after risk factors. Yeah? And so if you have to put some variables under things more complicated, then here comes back the statistician, okay? Because it's really modeling. It's not only looking at associations. And then this is what you get. For each patient in your cohort, you get a probability of being treated or not. And in fact, in your cohort, you have newborns who have been sedated and those who have not. And you look at their distribution of probability of being treated. That is to say that in treated infants, of course, the probability of being treated is globally higher, but there is some overlapping. It's to say that some were not treated as their probability of being treated was rather high, and some were treated as their probability of not being treated was high also, you see. So it's really, the idea is to see in the treated, there are some that had a high probability of being treated, but were not treated, and at the opposite, in the non-treated, some had a high probability of being treated, but they weren't treated. And the interest of that is that for the overlapping portion, you can compare one patient not treated to a patient treated with the high probability of having been treated. That is, you take into effect, for instance, it takes a bit into effect the severity of the baby. Some severe babies were not sedated, and some not severe babies were treated. And so for each patient in one camp, in one group, excuse me, you take one patient with the same probability score. So this gives, so you have different possibilities. Here you have a problem because you don't have any overlapping. And here everything overlaps, so you're going to compare all of them at the same risk of being treated. And here you have partial overlapping, but you're going to restrict to the overlapped. Yeah?
I have a question.
Yeah.
About the situation B over there, isn't that the sign that your variables really don't
predict? Absolutely. Absolutely. Well, yeah, absolutely. Don't predict. I'm not sure because the distribution is not absolutely the same. You have two things. Does it overlap? And do high probability. You see if well, this one is really overlapping, but here you have more infants with high probability and more infants with low probability. So it's not only the overlapping, but it's also the distribution. Does also the importance of probability here, is it the same on the other side? It's both things that intervene. Yes or no?
I think the overlap is in the distributions are on the
Yeah.
lower side. The lower side is bigger in the upper.
Yeah, but that's because the number of non-treated is maybe more important. Yeah. But even the probability of being treated here, you see it less often in the group B. Yeah. So, but this is not a very interesting situation. But you can still use it here. Here you can. This is the important situation, and here you can't use it. That's clear. But here it's not. You can't say that you can't use it, but because both completely overlap.
In the B situation,
yeah,
it's like a randomized trial. It's perfect.
Yeah.
What you find in reality is the C. And if you are lucky, if you have constructed a good propensity score, you find this. And right? Is it so? Because you are then constructing a propensity that is that independently of the fact that they are treated or not, this is what you estimate to be their probability first. So that probably within the same little...
in this zone is where you're going to be able to compare them.
And then you can have stratified with by the propensity score.
Yeah, I'm going to show that after.
Okay.
Yeah. So, and you also have to look at, because it contains information, what are these patients and what are these? Okay, just to try to understand why they are with a so low probability of being treated and a so high probability of being treated. It can help in understanding. Okay, and then after that, here's an example. We tried to look at PDA treatment and outcome at 5 years in EPIPAGE. And actually, it was really not overlapping. So we didn't go further on. And why? Because actually, when you do the cohort, it's not your principal question. And so these are most frequently post hoc questions. And so, in fact, here probably we are missing important variables that could explain the fact that they were treated or not. So if you don't have those variables, you can't build a model that predicts the fact of being treated or not. You understand? Here on the PDA treatment, we were probably missing important variables who permitted to predict the fact that they were treated or not. So this is why the distribution really don't look the same. And so it's not very reasonable to try to compare them even by matching on propensity score. So you have to look after a certain degree of overlap. Yeah. Okay. So now you can run the analysis between sedation and 5-year outcome, and you're going to do it adjusted on the propensity score. So finally, you're going to look at sedation and 5-year outcome, but at the same level of risk of being treated, which tries to resemble at randomization. So you're trying to get as if it was randomized, if they have the same probability of being treated. Okay? And you have three ways of, let's say, matching or look at the association at the same level of propensity scores. So the first one is matching. That is, for one patient in the sedated newborns, you will match another patient with the same propensity score. So this is individual matching. It's a way of doing it. The problem of this is that sometimes you don't find a matching point for some patients. So you can exclude, again, unmatched patients. And each time you exclude, you're selecting a certain type of population. But it can work. Aspirin and mortality, and so they wanted to see if aspirin could reduce mortality, but it was on a cohort of evaluation of known or suspected coronary disease. 37% of the population was under aspirin. And looking just at the association between aspirin and mortality, they found, a 4.5% mortality increase rate. But, well, treated and non-treated were different, as we saw in the EPIPAGE study. And so, after matching for propensity score, well, of course, they become comparable on these variables. Okay. So it's possible, and when it works, it's interesting. But it doesn't always work. So that was, you know, the risks of all these outcomes before adjustment and after matching. So, stratifying. Well, it's the same principles, simply you take groups. So you take all your patients and you divide them in groups of propensity score. Yeah. And in a group you will compare, and so it's stratified analysis. This has an advantage, is that it excludes a bit less patients. But you have to have a large cohort, because otherwise some subclasses may contain patients only from the treated or the untreated group. So this type of method applies on large cohorts. So in sedation and 5-year outcome, back to EPIPAGE, disability or death after discharge was significantly different and more important in sedated children. And so they stratified by probabilities, you see, those who had less than 11.6%, between 11.6 and, yeah, so those are terciles, for example. And after matching, it wasn't significant anymore. After stratifying, excuse me. So, And we looked at by strats of probability of being sedated, and really it's constant in every strats. You can adjust on it, and so you do again a regression with the outcome, the intervention, and here we're asking ourselves, is the intervention, sedation, influencing the outcome, 5-year outcome? And simply you adjust on confounders and on propensity score. So it's another way to do. There's a vast debate on should we put confounders, some of which could be part of the propensity score. I don't have the response. And what I saw in EPIPAGE, they did with and without, and it didn't change a lot. So it sets a bit sensitivity analysis. But I know it's some say you must, and others say, well, it depends. So I'm not sure. And finally, the advantage of propensity score when you do this by regression is that the propensity score resumes a reasonable number of variables. So you are a bit parsimonious, you see. Okay. Okay, that's what we said, and that was the result. And no adjustment. There was an increased risk of bad outcome at 5 years. If you only adjust on gestational age, it was at the limit of significativity, and on propensity, it was really non-significant. So it's, yeah, it's, I don't know how you say mud in English, but it's a fashion. Yeah, the number of publications with propensity score is rising. Yeah. Although it's not the only solution. And here you have randomized controlled trials and pediatric randomized controlled trials. Okay, so it's a bit difficult in pediatric research, but it should. Actually, what could be randomized should be randomized. But in generating hypotheses or exploring comprehension of some associations, propensity score could be used. So, when you are modeling, the first step, well, don't be too parsimonious. When you look at predictors of treatment in that modeling, just look at collinearity. That is, don't put two variables who mean the same thing. And we were discussing, I think, this morning, should I put age, gestational age and birth weight in the model? Well, it gives very similar information. And probably we said we should put rather growth restriction or small for gestational age, depending on what is your question. So you test the predictors for statistical significance, and you have to have large cohorts, honestly. So this is a problem. And then you have, this is the statistician part of the modelization, but they have to look at regression weights. Yeah, that's the statistician. You also have to try and run your model with multiple subsets of your population. That's what we call bootstrap, and it could be compared to a sensitivity analysis. And all this is statistician stuff, okay. What could be interesting if you really have a big cohort is to modelize on on a sample of your big cohort, a randomly determined sample of your big cohort, and then validate your score. Does it really predict treatment on the other part of your cohort? So this is interesting. When you have big cohorts, you elaborate your propensity score on a part of the cohort, and you validate it on the other parts. But these two parts have to be randomly determined. Of course, if you could, if you have another cohort where you could apply the propensity score, you can try to validate it. And again, this is a lot of statistics. And even if you can't apply all of those 9 steps, just look at balanced covariates and just, like we said this morning, just try to understand what all the variables you put in the model mean in a clinical sense. So the limits. You can only adjust on observed confounders. So again, we have the problem that if you are missing a few variables that are important determinants of treatment, your propensity score won't be appropriate. And if this is a post hoc analysis, you will miss a few of important variables. So this could also be said that if you plan to do a propensity score, try to think of which variables would be interesting to put in the propensity score at the moment where you plan the first study, the cohort study. Okay, and once again, propensity score doesn't eliminate all selection bias. You need large samples, and it doesn't always work. So, once again, the first step is to fit your propensity score. Does it really predict the threat of being treated? Secondly, you calculate your probabilities for each patient. And then you compare the intervention, the treated and non-treated, accounting for the probability to be treated. That's the idea. Okay, this is the same thing, never mind. I'm clear with the fact that randomized studies are preferable, okay? But again, if you're at the step of exploring hypotheses or on subjects where you can't randomize, I think it's an interesting technique. Yeah. Okay, so that's what I wanted to tell about propensity scores. I don't know if you have any questions, or is it a bit clearer than at the beginning? It's just to give you, you know, envie. I don't know how you say envie. At the end of the day, my English is declining.